also supervised the work of 10 PhD students. And his field of interest is classical cryptology, quantum computing, and quantum information insecurity.
Oh, okay.
I should add that he is a visiting faculty at our center. So I would encourage all of you to meet and discuss with him on topics of cryptology, cryptography, quantum computing, quantum information, and security. So now I'd like to request Dr. Paul.
Thank you, Vanuda, for the introduction. Okay, so we all know that monogamy of entanglement is a fundamental property, a fundamental result in some information, right? So this talk, we are going to see that sometimes it may not hold, right? So we know that it holds universally as of now, but I will show some cases where it does not hold, and then we'll try to look at it from the foundation point of view, and that what is its relationship with cloning and how does it affect the entire quantum paradigm. Okay, so okay, is it visible? Am I blocking? No, it's fine. Okay, so this is a quick breakthrough after introduction. I think some of the materials have been covered, I think 2 weeks back by 2 eminent speakers, Professor Agarwal and Professor Pati. So maybe I'll skip those. Then I look into monogamy of entanglement, entanglement measures, then some properties, then the relationship between monogamy and cloning. Okay. After that, we'll talk about indistinguishable particles. Then we'll come to our main result, followed by discussion. Okay. So when the quantum physics was beginning, right? Max Planck, when he started his PhD work, his advisor Philip told that it was probably not a great idea to study theoretical physics, since there was not much left to do, right? And the rest is history. So we know that at some point of time, it seems that a subject has reached its peak and it is saturated, but then some new results, come up, and then again the ball starts rolling, right? Okay, and this is a well-known 1935 EPR paper that raises questions about the completeness of quantum theory, and then 1964, Bell's famous result that shows that no local realistic theory can reproduce the predictions of physics, right? So here, local means that any particle is affected by its surrounding only, loosely speaking, and concretely speaking, that if there is a cause at a point A, then that cause to have an effect at a point B, right, will take at least the distance between A and B divided by the speed of light, that amount of time, because either a wave or a particle has to carry the cause to the effect, and the maximum speed of that propagation is bounded by the speed of light. So that's what is meant by locality, that if 2 points are at a distance, then simultaneously an event cannot have an effect, right? And realistic means, mathematically speaking, deterministic. That means you can predict the outcome. Given all the preconditions of an experiment, you can predict the outcome with probability 1, with certainty, right? And this 2022 Nobel Prize goes to Aspect-Clauser and Zeilinger because of their experimental verification of Bell's result. And in 2023 also the Breakthrough Prize, Fundamental Physics, because of contributions of Deutsch, Shor, Bennett, and Rasad, contributions of them to quantum information. Okay. And since Bell's time till now, there are many interpretations of Bell's theorem, and there are many versions of it. Like, for example, some version of it talks about free will, right? So, like Bell assumed that the experimenters who will be using the apparatus, right? They are free to exercise their choices when they will choose the measurement basis or the experimental parameters, right? So what is its connection, like whether free will can be assumed as an axiom or not? So all those things come under this paradigm. So there is a strong free will theorem, weak free will theorem, those things. But in this talk, we'll not go into those philosophical paradigms. So we'll stick to the common agreement that both the non-localist and also the what is called super deterministic paradigm of people, they agree upon. Okay, so we'll fix to that particular mathematical setting. Okay, so if we come to some correlations, then we have classical correlation on one side, and then the quantum correlations can be plotted in this diagram: Bell non-locality, stirrability, entanglement, discord, and coherence, right? So we'll stick to the entanglement scenario here. Now, because the talk is about monogamy of entanglement, we all know what monogamy means, right? It's like sticking to one partner in a relationship. So in the particle domain, it boils down to, like, if two particles are, let's say, maximally entangled, then none of them can share any quantum correlation, or actually speaking, any correlation, whether classical or quantum, to any third party. So that's the monogamy, right? So mathematically speaking, if E, this capital E, is suppose an entanglement measure. Okay. So EAB is the entanglement measure between A and B, and EAC is the entanglement measure between A and C, and EA, then the vertical line BC denotes the entanglement measure between A and the combined system BC. Okay. So the monogamy of entanglement says that if you apply the measure of entanglement on the system AB, and then you apply the measure on the system AC, then the sum of the two should be less than or equal to the entanglement measure between A and the system BC taken together, right? And you see that I have written the corresponding density matrices upon which the entangled measure will act, right? So between A and B, definitely it will be rho AB. Between A and C, it will be rho AC, and between A and BC, it will be rho. Okay, so those are the input states. An application of this result can be found in quantum key distribution, then classification of quantum states, condensed matter physics, black hole physics, etc., etc. Okay. So now, because we have talked about E, so there are certain properties that any entanglement measure should satisfy. So what are those? First of all, it should be 0 if rho is a separable state, because then the entanglement is 0, right? Then if it is maximum, the entanglement is maximum, then the value should be 1. Typically, that's the case. However, that is not listed as an axiom. The value should be maximum. We can normalize it to be. Okay. It should be invariant under local unitary transformation. So, for example, if so, here we are talking about bipartite measures, right? That's why we have this tensor notation between the operations U1 and U2, assuming that U1 is acting upon system 1 and U2 is acting upon system 2. So if we have U1, U2 acting upon the joint system, so after the unitary operation, the state, if the initial state is rho, then after the operation, the state can be written as U1 tensor U2 rho, then U1 dagger, U2 dagger, right? So if we apply the entanglement measure on that modified state, it should give you the same entanglement, right? So that's the thing. Then again, entanglement cannot be increased by local operation and classical communication. Okay, so okay. So if this inequality is satisfied, then Oh, okay. Explanation of says that suppose this E is maximum, okay, between A and B, this measure. So in that case, this E will be 0. Between A and C, there will be no entanglement. Okay. So A simultaneously cannot be maximally entangled with both B and C together. So that's the physical meaning of that. Okay. Mm-hmm. Yeah. So for example, the E function has a fixed maximum value, right? So for example, let's say it is 1, it is normalized to 1. So, okay. Okay. Right. Right. Less than equal. So right side will be 1, A between B and C. It can be also be larger, right? No, so see, so it does not. Okay, I'll come to the equality version of this very soon. So inequality. Okay, so when inequality happens, right? That is the non-maximal case. Now, what I'm saying is that when the inequality holds, when the strict inequality holds, then the entanglement is not maximal. Okay. When strict inequality holds, the entanglement is not maximal. The sum of these two can be 1, right? No, so yeah, it can have so half plus half equal to 1. So that is possible. That is possible. That is possible, right? No, E. So E cannot be larger than 1, right? Yes. No, what I'm saying is that, okay, so one possible case is that this is less than 1, this is less than 1, and the sum is also less than or equal to 1. Okay, so that is a valid case. I hope that answers the question. Okay, thanks. Okay, so then the entanglement measure function is convex, and it should follow the additivity property. So this just comes that if suppose I have n copies of the state row, right, and I'm applying the entanglement measure, then it should be additive n times the measure. Okay, so concurrence is a very popular measure, the squared concurrence. So it is defined as given any density matrix rho, if we apply this matrix capital R, if we have this matrix capital R, right? So then the eigenvalues can be written as lambda I in decreasing order. So lambda 4 is the highest eigenvalue, lambda 1 is the lowest eigenvalue, and it can be shown that these eigenvalues are non-negative. So we can take positive square root of these eigenvalues, and so the value of the concurrence is defined to be maximum of 0 and this quantity, right? And this has been proposed, this measure has been proposed and discussed in this famous paper, CKW paper 2000, right? That talks about distributed entanglement. Okay, fine. So here is one example that monogamy actually, though we know it to be universal, depends on the measure, though most of the measures, most of the valid entanglement measures will satisfy it, but actually depends on the measure and also the dimension of the system, right? So for example, that for Q traits, so we go to dimension more than 2, then the same squared concurrence measure, monogamy is violated. So here is an example that if we take this state as the 3 particle state, then C square AB plus C square AC, it can be shown to be 2, which is greater than equal to 4/3, which will come as C square A given BC, the squared concurrence entanglement measure, right? So, but if we take a squashed entanglement measure, that is another instance of E, then in this dimension, monogamy will be, holding. So that leads to this definition of monogamous entanglement measures in qubit, right? So squared concurrence, log negativity, entanglement of formation, then Chalice-Q entropy, etc. There are many which actually follows monogamy, and there are some measures which may not, right? So now Emax we define to be the maximum value of the entangled measure E. So violation can happen in two ways. So non-maximum violations, if the monogamy inequality we get, say the individual values are less than max, that example that you were giving, right? But the sum is greater than the maximum. If it happens, then it could be one violation. Whether it will happen or not, that's a different question. And maximum violation is that if individually both AB and AC becomes Emax, right? Then the sum is 2 Emax and the right hand side cannot exceed Emax. So therefore it is a violation. Right. Okay, next we'll see the connection between monogamy and cloning. We know that cloning is not possible in classical domain. Cloning is possible in classical physics, but it's not possible in quantum domain because of linearity. So no cloning theorem says that if we have a cloning machine U, right, and if we have psi, the input state 0, and it produces the states 2 copies of psi, right, then it leads to the fact that either we can have cloning machine for pairs of orthogonal pairs of states, like, so there will be for psi perpendicular there will be one cloner, then for another state and the perpendicular of that state there will be another cloner, like that. So there cannot be any universal cloning machine. So if the input state is unknown and arbitrary, such a U cannot exist. So that's what the proof is, the famous 1982 paper, and this is applied in quantum error correction, quantum cryptography, black hole physics, etc. Okay, so the next interesting fact is the connection between monogamy and cloning. It is often encountered. I have seen that in many papers of quantum physics in the introduction, it is loosely stated that monogamy and cloning are equivalent, or they imply one another. So this is a brief look at that fact. So in this slide, we are going to argue that maximum violation of monogamy implies cloning. Okay. So how is that? So suppose maximum violation of monogamy is holding. That means A is simultaneously having maximum entanglement with B and C. Okay. So that's the assumption. So this dotted curved line is showing max. Now, suppose we have an input state phi x, right? So what we can do, we can actually do a teleportation like protocol. Like we know that in teleportation we have a Bell pair, right? And using the Bell pair, we can create a copy of the state at the destination, right? So you can think of AB as a teleportation channel. So using the channel AB, we can create, and using the unitary U at B's end, we can create a copy of phi x, that is phi B. Okay. Similarly, using the teleportation channel AC and using the unitary at C's end, we can create another copy of phi x, that is phi C, right? So now these two are two copies of the unknown state, and it violates cloning. Because to have this copy created at the other end, we just need perfect entanglement, maximum entanglement between AB, right? That holds, and between AC that holds separately because of the assumption, and it leads to cloning. So here maximum violation of monogamy implies cloning. On the other hand, suppose cloning occurs. Now, does it imply maximum violation of monogamy? So the argument is very simple. Suppose A and B are maximally entangled, right? So now we assume that cloning holds. So you clone B to create B prime. Now cloning will create all the properties identically, right? So B prime will have exactly the same properties as B. Now since B is maximally entangled with A, B prime being identical with A in all aspects must have maximum entanglement with A as well. Therefore, A is maximally entangled with both B and B prime, which violates the monogamy principle. Okay. So indeed, we have seen that from this analysis that cloning and maximum violation of monogamy, they do imply each other. Okay. Okay. So now I will show an apparent violation of monogamy. So which is a violation in one view, but in, I would say, more finer view, it is not a violation. So if we talk, if we consider degrees of freedom more than one, okay. So suppose each particle has 2 degrees of freedom. So now particle A and B, they are maximally entangled in their first degree of freedom. So it can be spin or angular momentum, or it can be spin and path. We can have multiple degrees of freedom. And particle A and C, so the A2 degree of freedom, the second degree of freedom is maximally entangled with the second degree of freedom of C2, with C. So A and C, their second degree of freedom is maximally entangled. A, B, their first degree of freedom is maximally entangled, right? So from the particle point of view, A and B maximally entangled, because when maximum entanglement happens, then it is assumed implicitly that some degrees of freedom we are talking about, right? Between A1, B1, it is maximally entangled. A1, B1, right? Yeah, that's the typo. That's the typo. It should be A1, B1. Then A2, C2 is Emax. Okay. So this type of state is called hybrid, and it's called hybrid. Sorry, this is called hybrid, and this is proposed in Chitrabhanu et al. 2015 paper. So this apparent violation can be resolved if we rewrite the monogamy inequality in terms of degrees of freedom, not in terms of the particle, right? So actually, degrees of freedoms also behaves like particles. So for example, if you have one particle, you have 2 degrees of freedom, right? You can associate quantum state with degree of freedom 1 and another state with degree of freedom 2. You can talk about the joint state, so which can be represented in the Hilbert space, which is tensor product of both the degrees of freedom spaces, right? So in that view, degrees of freedom are nothing but particles, and if we label the degrees of freedom as I, suppose there are n degrees of freedom, right? So I can vary from 1 to n. We can just write the indices that, okay, if AI and BJ are maximally entangled and AI and CK are maximally entangled, right? Then, sorry, not maximally entangled. I mean, the monogamy inequality can be written in this manner, that we have to the monogamy inequality, or let's say the violation, whatever is talked about, should be on the same degree of freedom. So if we are talking about, let's say, A5, then if A5 is maximally entangled with, let's say, B5, then A5 cannot be maximally entangled with any other degree of freedom. So in this case, it does not happen, right? So we do not have arrow going out of A1 or going out of B1 or going out of C2 or A2, right? So they are disconnected. So that's what is this. So this should be kind of the refined monogamy equation, and then the apparent violation is resolved. We'll move into some example of actual violation of monogamy, okay, and what are its implications. So for that, we have to look into what is called indistinguishable particles. Right? So particles are broadly classified into 2 categories: non-identical particles and identical particles. So identical particle means if all their intrinsic properties are exactly the same. Like for example, 2 electrons, like 2 photons, right? They are identical. Whereas 1 electron and 1 proton, they are non-identical. Okay, so that's the typical example. Non-identical particles are always distinguishable. Now, identical particles, they may be distinguishable or indistinguishable. So indistinguishable means that each particle cannot be labeled individually. So I cannot say, okay, this is my first particle, this is my second particle, this is my third particle, or this is my left particle, this is my right particle. I cannot label them. Okay. We'll see how indistinguishability can be created. Okay, so suppose S1, S2, S3 are spatial locations. There is a particle A in spatial location S1 and particle B in spatial location S2, and their wave function are separated. So the square blue represents first DOF, and the triangular red represents second DOF. So it's a 2 DOF we are talking, because we'll be using it later. Now, suppose both the particles are brought in spatial location S3. Okay, so then their wave functions will overlap, and when they are at S3, we cannot say that which one came from A and which one came from B. Okay, and this indistinguishability remains if they are separated later on. Okay, so even if now they are separated, because as if some kind of mixing is happening here, right? So when we move them apart, so when again I have one particle in S1 and I have one particle in S2, right? And suppose this mixing is happening in some kind of box, right? As if you are having two balls, right? From left and from right, they are externally looking identical color and shape. You are putting into one box, then you are shuffling the box, right? So that's spatial location S3, and then you are taking the two balls out. One you are moving to the left, one to the right. Now you cannot say that the one that you are having in the left region was indeed originally in left. You cannot say, right? So quantum mechanically, if you have to write the wave function, it has to be kind of a superposition of both the left and right, and so on the right hand side. Okay, so now distinguishable particle and indistinguishable particle, they do have some strange similarities as well as dissimilarities. Okay, so let's talk about the properties, quantum properties or quantum applications that we know. For example, coherence, is a property, right? Steering is a property. Metrology is an application. Then quantum teleportation, you can think, is an application, right? HHES means hyper-hybrid entanglement state, where you have cross entanglement between two different degrees of freedom as well as 10 degrees of freedom. So, this is our work in 2020. So prior to 2020, there were a bunch of works which showed that, some quantum properties that are known to hold for distinguishable particle. Now, it is not known whether those properties or applications are possible with indistinguishable particles. So now there are a series of works that shows, okay, coherence, it holds for indistinguishable also, or steering is possible for indistinguishable also. So because there are a bunch of works before 2020, it was kind of conjecture that, okay, distinguishable and indistinguishable particles, they will have same properties or same applications, but maybe the efficiency will change, right? The capability might change, and there are some numerical results to explain that. Okay, all the properties hold, but with some degree, the degree variation. Now, that does not quite tell that these two sets of particles are different. Like if we find some unique property or unique application that holds for one kind but does not hold for the other, then we can say that really there is a separation between the two. So we call this a separation result. Actually, two separation results we showed, where this unique fidelity quantum teleportation, that is something which holds only for distinguishable particle. It does not hold for indistinguishable particle, right? So that is one separation result, you can say. Another separation result is that hyper-hybrid entangled state, that is possible for indistinguishable particle, but that is not possible for distinguishable particle. So we have the proofs here. However, this is not related to the monogamy thing that we are going to say, but the violation that I'm talking about of monogamy, that will be shown with respect to indistinguishable particles only. So to cut the long story short, that before like 3-4 slides backwards, when I talked about apparent violation of monogamy, and then resolve the apparent violation looking at the degree of freedom view than the particle view. So up to that point of time, all the results that I discussed, including the equivalence of monogamy and monogamy violation and cloning, all those things actually apply to distinguishable particle, right? So all the proofs and all the arguments, nowhere it explicitly says that it holds for distinguishable particle, but it's implicitly assumed. Now, what we are going to show that this violation, it holds for indistinguishable particle, right? And then we'll discuss what are the implications and what are the results. Okay. So this is kind of cluttered notations. I'll not go into more details. So you can. So these notations were introduced by Lo Franco in 2018 and Lorenzo in 2019. So basically, if you look at simply that alpha and beta are spatial locations, okay? Then A1, A2, these are basically degrees of freedom. B1, B2 are degrees of freedom. So A1 is denoting the first degree of freedom, A2 is denoting the second degree of freedom, and these are variables. That means A1 can range over a bunch of values and A2 can range over a bunch of values. Similarly, on the other side. And this notation that, one spatial location, then some values of the degree of freedom, comma, other spatial location and some values of the degree of freedom, that is kind of the notation for indistinguishable particle. In general, you can have a superposition of all of that. So for example, if you have the left and right mixing, right? So the state can be left and right both, combination of left and right both, right? So that's kind of the understanding here. And the density matrix can be written analogously. So what, okay. So, since 2018 and 19, there were certain definitions and properties that were derived for indistinguishable particles. So for example, how the, let's say, measurement should happen, okay, how the inner product should be taken. So those works were done, but how the trace out operation will be done, particularly for degrees of freedom, that was not there in the literature. So what we introduced is the degree of freedom trace out rule for indistinguishable particle, right? And that's non-trivial. So I'm not going into that, but using that degree of freedom trace out rule, because you see that if you want to apply entanglement measure on part of a system, right? So if you have A, B, and C, right? If you want to have entanglement measure between A and B, then you have to leave C out, correct? If you have to have entanglement measure between A and C, you have to leave B out. So in some sense, that trace out is needed, no matter what kind of entanglement measure you are using. So DoF trace out rule is important because we are applying the entanglement measure on degrees of freedom. Why degrees of freedom? That was already justified, because if we look at particle level, then we may be under delusion, right? Because there may be apparent violation. We should look at that the same degree of freedom of one particular particle is entangled to both other degrees of freedom or not. So here we actually show that it is possible to have such kind of entanglement in indistinguishable particle. Specifically in qubit system, indistinguishability is a necessary criteria for maximum violation of monogamy of entanglement by the same measure. So this is important because we mentioned that even for the distinguishable particles, right, monogamy, whether it holds or not, will depend on the measure and the dimension. So here we want to show, actually we show that the violation of monogamy occurs by the same measure that are known to be monogamous for distinguishable particle, right? So unless we are using the same measures and the same dimensions, then we cannot claim that yes, it is a different result. It's something which is different from the distinguishable. So that's what is the meaning of this theorem. And this is kind of a schematic to demonstrate that it really holds. So basically what is happening, you see this ash color shaded region is Alice's side, and the light yellow shaded region is Bob's side. Okay. Now both of them start with a spin down particle. Okay, so Alice has one spin down particle, Bob has one spin down. Now it goes to hybrid beam splitter. So I will show the circuit of hybrid beam splitter on the next slide. But what physically it does, whatever beam splitter does on 1 degree of freedom, hybrid beam splitter actually splits the state in multiple degrees of freedom. So for example, here, if I have a down spin, right, and it is coming to, it's moving to right direction, right? So after hybrid beam splitter, it will be right and down both. So just like if you have horizontal polarization, right, after it passes through beam splitter, you have half 1/√2 horizontal plus vertical, right? So one horizontal state gets splitted into 2. So similarly, and the spin, the down spin will be splitted into up and down, that combination. Okay. So right gets splitted into down and right. Similarly, here at Bob's side, we have hybrid beam splitter. So here left gets splitted into upper and left because of the hybrid beam splitter. That's the path degree, you can say. And the spin degree gets splitted into the down, becomes combination of up and down. And then we have okay. So after that, so this left part comes to Alice's side, this right part goes to Bob's side, and then this phi r, phi u, phi d, and phi l are basically local phase shifting operations. So why you have parameterized by d? Because this is working on the down path, this is working on the left path, and so on and so forth. So Alice can control phi d and phi l, like what, how much will be the phase shift on both, and Bob can control these two. Okay, then Alice has choice that okay, after application of phi d and phi l, there is a further option for Alice to do the spin measurement. So this is the schematic for spin measurement, or Alice can do the path measurement. Okay. Similarly, Bob can do the spin measurement or the path measurement. Now, if Alice does the measurement pathwise, then Alice can have values. Okay, let's say, okay. So from Alice's side, if Alice is doing the path measurement, Alice can have values either L or D. If Bob is doing path measurement, then Bob can have value either R or U. So those are the eigen states for Bob. For the spin, both can measure up and down. So basically, path has 4 values. For the path degree of freedom has 4 values here: down, right, left, and up. And spin degrees of freedom has 2 values: up and down. Okay. Now this is the schematic of the hybrid beam splitter. We have polarization beam splitter and quarter wave plate, 2 polarization beam splitter and 2 quarter wave plates. So, and 2 mirrors. So basically, this simple combination. And this was not something new which we proposed. This was already there, existing, 2018. Okay. Then in the notations of indistinguishable particle, you can write the above state, and then we can show that by controlling these 5 values, you can actually change the correlation between them. And using concurrence measure, so this is S1 and S2 are the 2 types, right? So A and B are the degrees of freedom. So A2 and B2, and A2 and B1. So you see that this A2, the site S1 and degree of freedom A2, both are maximally entangled with the degree of freedom B2 of site S2 and degree of freedom B1 of site S2. Okay. So the question is that now which one is more fundamental, right? No cloning theorem or monogamy of entanglement, because both were known to be equivalent to one another. So what we claim after this work, that because with indistinguishable particle, we have shown that they violate monogamy of entanglement under certain settings. So we're not saying that all indistinguishable particle will violate, right? You have to have this certain kind of apparatus. So this is called a particle exchange method. So particle exchange is a way to actually mix, 2 particles and make them indistinguishable. For example, here we have path indistinguishability, right? Because of the mixing. So the point is that, so that means you can construct some mechanism which will show violation of monogamy for indistinguishable particle, right? Now that violation, we argue in the paper that in distinguishable particle, violation of monogamy implies cloning. So naturally, the reviewer asked that for indistinguishable particle, why does not it imply cloning, right? So we connected it to the teleportation fidelity, right? So it is known because of the prior work that unique fidelity teleportation is possible only for distinguishable particle. For indistinguishable particle, it is not possible, right? You can show that if you can do that, then actually it violates special theory of relativity. So there is an argument behind that. I'm not going into that. But because unique fidelity teleportation is not possible using indistinguishable particle, so you cannot have a perfect teleportation channel using indistinguishable particle, and therefore that cannot clone. Even if you have maximum violation of cloning, maximum violation of entanglement, you cannot use that to actually create two copies at the two sides with perfect. So you can create copies, but with imperfection. So that means perfect cloning is not possible, because cloning also will have a fidelity definition with itself. So when the no cloning theorem, what it actually claims is that perfect cloning is not possible, but partial cloning is possible. That particular theorem does not talk about. So here, indistinguishable particle may give partial cloning, but not full cloning, not with probability 1. Okay, so that's one aspect. Second point is that one may ask, why does no cloning theorem, okay. Second point is that then can we say that no cloning theorem is more fundamental, because no cloning holds both for the distinguishable and indistinguishable particle? So it seems that yes, it is more fundamental than monogamy. So if you consider both the sets of particles, the whole paradigm of distinguishable as well as indistinguishable particles, right? If we consider that, all of that together, the entire quantum paradigm, then no cloning theorem seems to be more fundamental. And if you look at the proof of no cloning theorem, it does not use distinguishability or indistinguishability, right? It simply uses the linearity of quantum mechanics. So that proof is more foundational, so to say. Right. So second point, what is the application? What is the application of is missing here, of this maximum violation of monogamy? So we are trying to find out how this maximum violation can be applied. What are the implications? So for example, in quantum cryptography, many security proofs depend on this monogamy, the monogamy principle. So for example, suppose Alice and Bob, right? They are sharing something, yes, sharing some secret. So we show that, for example, in Eckert-like protocol, right? We argue that if Alice and Bob are perfectly entangled, maximally entangled, then it is foolproof, because the monogamy prevents any third party, Eve or attacker, to have even a classical correlation, right? What to speak of quantum with either Alice or Bob. Then that will violate the monogamy principle. So by monogamy principle, Eve cannot have any correlation with Alice or Bob, and therefore the communication between Alice and Bob is perfectly secure. So that kind of proof argument will not work for indistinguishable particles, right? So does it imply that if indistinguishable particles are used to construct crypto protocols, then they become insecure? So we are currently looking into that thing. So it's not so straightforward, because there are other issues of indistinguishability, right? Like, for example, the teleportation fidelity does not give, right? There are some other properties in distinguishability which holds inefficiently in indistinguishable particles. Okay. Third question is that whether this violation is possible for other quantum correlation, right? Other than, for example, monogamy is shown to hold not only for entanglement, but also for other properties, like steering. There is steering monogamy, there is coherence monogamy, discord monogamy, etc., etc. Many versions of it. So whether violation can be shown in those properties also. So that also we are currently studying. So these are the questions that I proposed and I answered myself. So if you have any other questions, I'll try to answer. And by the way, my ex-PhD student Shomo is present here. Shomo, who is now working in TCS Quantum Lab. So he did most of this cluttered computations by hand in this paper. So if you have a numeric question, you can ask him. Any question from the online audience? Achha, you have a question. Mike, can someone?
Within ABC, is there any prior relation between B and C?
Prior relation means?
Like they are in or some kind of relation, or they are totally separate?
No, so between ABC, that kind of inequality that we are showing, right? That's for always, right? So at any point of time, suppose they are not entangled or they are partially entangled, or there is this entangle between all three of them. So they will evolve, right? Using, either you will apply some operation or they will interact with environment, they will change. So no matter whatever is the initial configuration, that time also monogamy will hold, no matter what kind of operations you apply and whatever is their, post operation state, then also the monogamy or that particular inequality will hold. So it doesn't rely on any assumption.
Okay.
For the concurrence measure, for distinguishable particle, for concurrence measure in qubit, there is no violation. It can happen only in Q3, and for that kind of state. So it's kind of an constructive example to show that in Q3 it may be violated. It's not that all kind of Q3 states it will be violated. That is also not the claim. Yeah, actually, we have talked to some experimental groups for verification of these results. It has not been done yet. So we published it in 2021. So no other groups also have done it so far that we are following.
I have a question. So you're saying for a particular measure for distinguishable particles, entanglement can be, the monogamy can be violated, right?
Yeah, actually, yeah. So just hold on. I must say that in general, whenever we talk about entanglement measure for, let's say, distinguishable or whatever particle, typically it is implicitly assumed that we are talking about monogamous measures only. Okay, because otherwise they are not much of use. Like,
yeah, that's what I was thinking, because regardless of what measure we use,
right,
entanglement is actually a physical property.
Exactly.
So that holds. So that will be violated regardless of the measure, only in case of indistinguishable particles. Is that what I understand?
Correct. So actually, we show in the paper, though the numeric calculation is shown using concurrence, but then we also show that all the other monogamous measures for which it will hold in distinguishable setting, we have the violation in indistinguishable setting. So the parallel is between, you have a monogamous measure that becomes non-monogamous in indistinguishable setting in the same dimension. So that's actually the claim.
All right. So the other question is, you can have maximal entanglement between A and B and A and C as well.
In indistinguishable setting, you cannot talk about A, B, C.
Okay.
Like, so here you can talk about because you are
identical.
Yeah. So yes.
So is it possible to have? So if you have, let's say A, B, C, of course we don't.
You cannot label, but yeah, after the particle exchange, after mixing, one particle is moving to the right, one particle is moving to the left. So that time you can say, okay, in the left half or in the Alice's lab, whatever particle we have. But this is not actually original A, right? Because A and B have been mixed now.
Yes. Yes.
Yeah.
So can it be entangled to another fourth particle again maximally? and or this has not been explored? I'm just generally curious because this thing
Keeps on, right. So
keeps on-
actually we were thinking about that because in distinguishable setting, like respecting the monogamy,
Mhm,
like you can how much entanglement you can create, like there are some results, right?
mhm,
So like, or with n number of particles, how it changes, and etc., etc. So here also we are kind of exploring that whether it can be stretched. Like it seems like we can have infinite number of maximum violations, right? Whether it will really hold or some physical property will prevent it
mhm.
from holding. So that needs investigation, but it's a really interesting question. We had it in our mind.
Exactly, because for 3 particles, we
Correct.
know that maximally entangled is the GHC state, for example.
Right.
Right. But in this case, we can have maximal entanglement between A, B, as well as B, C, which means the overall
Yeah, in principle, if
entanglement is actually greater than GHC.
if we can have maximum with A and C, it can also have with D and E and
Yes,
right.
yes,
It seems like, but we have to
right.
check
Because even in the 3 particle case,
that.
it exceeds the entanglement that is there in GHC state.
Right.
Which we know,
Exit.
which we know as the maximal entanglement.
Right, for distinguishable case.
Yes, yes.
Right.
All right, that's all from.
You talked about entanglement measure in the
Mhm.
definition of monogamy. Is it some way of quantifying entanglement? Between-
Yes. So that's why those requirements are there. No? That if you have separable state, then if you apply the entanglement measure, separable bipartite state, if you apply the entanglement measure, it should give the value 0.
But if there are so many measures, then how do you decide which one quantifies entanglement the best?
No, actually, see, all monogamous measures are equivalent, and practically, the squared concurrence is the most commonly and widely accepted popular measure in the community. Okay, both in the theoretical paradigm and in the experimental paradigm. So, if you want to show something, you have to use squared concurrence, and then you can argue about other measures. That's typically the consensus, I would say, in the literature. I think another question.
So you said it seems no cloning is the more fundamental. Sorry,
Yes.
than-
No cloning is more
than the
fundamental than
monogamy thing, right?
Correct.
Also, does it have, because it holds for the indistinguishable case, you said, does it have to do anything with bosons and fermions in just in case, like anything
For
to
the
do
no
with
cloning?
No, I mean the violation of.
No. It can hold both. The maximum violation of monogamy is possible with bosons as well as with fermions.
Okay. As long as they are indistinguishable.
Yes. As long as they're indistinguishable. Actually, the boson and fermion, the difference is the symmetrization, right? So instead of plus, you will have alternate plus minus. That's all. But when you have the squared concurrence, the values will not change. Correct.
So the circuit is shown for the violation of monogamy.
Mhm. Okay. Yeah. This circuit. Okay. So basically, in this setup, Alice has choice of spin measurement, which will give up or down, right? And choice of path measurement, right? Which will give either left or down. Then Bob has choice of spin measurement, right? Which will give which will give up or down. So the spin up and spin down, and choice of path measurement that will give up or right? And then you can do the coincidence statistics. So here the assumption is that you are having this, you are repeating the experiment with similar identical particles. Like that's why spin down, Alice side, spin down, Bob side, right? So suppose you have 1,000 particles, right? And you are measuring, let's say, the path degree here on the Alice's side with the spin. You find the coincidence, right? So spin and path, spin Alice and path Bob. And then again, you have another set of 1,000 particles, you have spin and spin measurement, but starting with the same identical initial state, right? Otherwise, you cannot claim that the final states are also same. So then you can show that yes, it holds. So that's kind of will be the how the experiment should work, right? But for theoretical argument, definitely you do not need the coincidence count. You can argue from the state itself and then density matrix, doing the trace out operation and applying the measure. Okay. So that's why how practically experimentally verified, that we have clear picture, but because we don't have a lab, we are trying to collaborate with someone who is interested to verify. With photons would be, I think, easier because boson. Right.
I think it's more distinguishable in some sort of
No.
these particles.
How? Because actually it is creating, see, it is actually creating more uncertainty, because it was before entering the hybrid beam splitter, let's say the path degree of freedom had value only right. But from the output of hybrid beam splitter, it is now a mixture of right and down from path point of view. Correct. So it is not creating distinguishability. And spin also, it was spin down. Now it will become a combination of spin up and down. So the beam, so it's a beam splitter for the spin and it's a beam splitter for the path. So that's why it's called hybrid beam splitter. It's working simultaneously. And this is known from 2018, and this has been experimentally verified also. The hybrid beam splitter that is used in experiment. It's quite common.
There is a recent paper on this, which tells that when you have introduced a polarization beam splitter, for example,
okay,
it actually so when you have indistinguishable particles or photons, you have tendency to bunch. So bunching effect because of the Mandel effect, we see then, right? But when you introduce this PBS in between, it actually reduces that. So because you are kind of creating a distinguishability in this whole circuit.
Okay, so then you are talking about, are you talking about particle count? How does it affect?
Yes.
Okay, I understand. So like you have that whether 2 0 or 1 1, that kind of setting, right? So that is kind of entanglement between spatial modes, but we are not talking about that here. We are not, the count. So like 1 1, like 1 0 plus 0 1, that kind of state where 0 and 1 are particle counts, that we are not considering here. So that is different. That actually is a distinguishable state. You are correct. That's a distinguishable state, but that's why we are not considering that state. Thank you.
Thank you.
Yeah, of course. For photon, it will be polarization. Thank you.